Okay, so live from Pittsburgh. This is the Monday lecture for modern algebra, and I'm picking up right where we left off. Actually, I'm going to go back and cover some of the stuff we did on Friday, just to kind of refresh your memory. So we kind of left off with example 24. There we are. So we've been talking about cosets. So we'll go back to this dihedral group D4 of order 8 that we've looked at before many times. The Cayley table can be found in your book, and I'm looking for the Cayley table now. Where the heck is it? The Cayley table is on page 118. So it's a rather lengthy Cayley table, but there it is. It's on 118. It's a dihedral group of order 8. And as we've looked at before too, from that same thing, the center of the group are the elements E and B. So here's where we get into some interesting things. So first of all, it turns out that the center is a normal subgroup. And since it's a normal subgroup, we can then form this group that's called a factor group, okay? And it is a factor group of D4. So again, this comes from definition 24, which says if H is a normal subgroup of the group G, then the group G slash H is said to be a factor group of G. And you can see in theorem 22 how this factor group is formed. I'm not going to go that far back, but anyway, so we want the right cosets of ZD4 in D4. So that is we take ZD4, all right, and we act on elements of D4 from the right. And there are some redundancies, and there are some things that just flat out don't work. But if you do this, you find that you end up with four elements of this right coset. So ZD4 acts on E, and you just get ZD4 back again. If you act on, again, acting on it from the right, so you act on it on the element A from the right, and you get EB acting on A, which is, because we're acting on it from the right, the A goes into the B there, see? So you have your new set is E comma BA, all right? And looking at the Cayley table, BA is C, and so our ultimate set there is AC, and we're going to label that with a capital A. And do the same thing with the B there. So you've got the center acting on D from the right, and that is E comma B acting on D from the right, which means the B acts on the D. So you have E comma BD, and from the Cayley table, this gives us DG. And you can keep sort of going through. Notice, by the way, all right, so let me just back up a second. So the right coset, so look at the one prior to that. You have E comma BA. Now, BA is C, right, according to the Cayley table. And so the new set is made up of A and C. The E, you just forget. E is just the identity, okay? And it doesn't really do anything there. And we're just interested in what the A is really doing, okay? And the BA, B acting on A, produces the C, okay? And so the new set becomes A, which was this thing that you were acting on, and the C. Same thing with the DG and the FH, as you can see as you go down, all right? And so those four sets then form the Cayley table for this factor group, okay? And in fact, and you can see that in page 140 and 141, it actually happens to be exactly the Klein 4 group. I would highly recommend going through this again as carefully as possible. I think this is a really important important thing. And in fact, what I would do is I would go back and take a look at the definitions of what it means to be a coset, which would require you to go back to the beginning of section 4.4 on page 127 and 128. And that's, you define there, they define the right and left cosets. And I'm trying to see if they, I don't think they really, he doesn't really give too many really good examples of this until later, of a right and a left coset. But I think the basic gist is made pretty clear by the definition. Okay, and you'll note that the right and left cosets are only equal if H is a normal subgroup. So in the sense, in this example, I've said the right cosets, but these are also technically the left cosets because the center is a normal subgroup. Okay, so there you go. If you have any questions on that, we can talk about it when I get back. But I think it's a really important example, and I think it really is important to try and go through that a couple times to make sure that you understand it. Anyway, I think I did the first isomorphism theory in class 2, but I'll just give it now. So if you've got G and H and they're groups, and you have some function that maps, say, from G to H, and we know this function is an epimorphism. So again, what is an epimorphism? Well, we need to go back to the definitions of, so we're talking about homomorphisms. An epimorphism is a homomorphism that is surjective, okay? And in fact, epi means, it's the Greek for upon, okay? Monomorphism is injective, and that's mono, alone, right? Okay, so that makes sense. So epimorphism, this function is an epimorphism, and it has a kernel K. And remember what the kernel is, if you have a homomorphism, the kernel is the set of all elements that the homomorphism maps to the identity, okay? So K are all the elements of G, all right, that under this function end up being the identity in H, okay? So if that's true, then this G slash K and H are isomorphic to one another, okay? Now, isomorphic means that there is some sort of mapping going between them that is bijective, okay? Another way to look at it is basically G and K and H are roughly the same thing, or they're represented in the same way, okay? And G slash K is, again, this factor group, all right, which is described in Theorem 22. So I walked through the proof in class, but I'll go through it again a little bit, and I add a little bit to the diagram that he's got in the book here. So f is some function that goes from G to H. And G is some function that maps from G to this GK, right? And there's some isomorphism between H and GK, all right? So one of the ways of looking at the proof is, so suppose we've got KA, where A is an element of G, and KA is an element of GK, all right? We want a mapping, H, all right? This is going to be our isomorphism, that maps from this GK to H, all right? Okay, so this is, we're trying to prove that GK and H are isomorphic, all right? So essentially, to do that, we want to look for a mapping, that represents an isomorphism. And if it is isomorphic, it means that h of Ka is equal to f of A. Okay, where A is still an element of G. All right, and again, Ka is an element of Gk. Right. Think about that second sentence very carefully. It'll really make sense if you just stop and think about what that means. So we basically want to find a mapping that goes from Gk to H. That basically when you stick Ka into it, it's equivalent to having this function from G to H that you just stick A in. All right. Now, that means that Ka must be equal to Kb, which means that f of A equals Fb. But if Ka and Kb are equal, that implies that B is equal to Ka, which means where K is some element of K. So you've got this f of B equals f of Ka equals, and then you can partition it f of K, f of A, all right, which is equal to the then identity in H times Fa, which is Fa, okay? And what that means is that our definition that we've chosen for this is sound, it's valid, okay? I'm not going to go through the too much more of the proof because I did do that in class. But the, well, yeah, actually, I guess I am. Look at that. I have another slide. So, so let's take a look at two things. So let's take a look at this, first of all, the surjective aspect. So let's say you've got an element of H. And, oops, I misspelled since. Well, anyway, it's supposed to be since F is an epimorphism, okay? There's got to be an element of G such that F of A is equal to C, all right? So, again, if F is an epimorphism, all right, it's some sort of a map, all right, that, again, think of it as a meat grinder. You take A, you drop A into the meat grinder, and it spits something out, F of A. And we're saying that if F is an epimorphism, then F of A, we're just going to call it C. Forget about whatever it is. We'll just call it C. But that means that we also have to have another meat grinder where we drop Ka in. All right, this meat grinder is called H, and we drop Ka in. And that's equivalent, and we get HKA out. And it's got to be equal to C. Okay? It's injective, all right? So that's the surjective part, all right? The surjective is the onto. The injective is the one-to-one. You've got HKA and HKB being equal to each other, all right, and FA equaling FB. And of course I missed a parentheses here, but say you've got F, and then in parentheses you have A, and then the inverse of B, all right? Well, that's got to be equal to FA, F inverse B, and actually it's FB inverse, which is the same thing as FB inverse. And all of that has to equal EH, which means that AB inverse is an element of K, and Ka equals KB. All right, so we're all set there. So basically what we know is that H is surjective and injective, which means it's bijective, okay? So it's one-to-one and it's onto. But how do we show that it's a homomorphism? Well, this is like the big thing to take out of this. What's the criteria for homomorphisms? It's basically that they behave like this. FAB is equal to FA times FB. Okay? In fact, those of you in real analysis have seen, we've been talking a lot about this. This is the character identity, again, which is just an equation, and it has a solution. And exponentials happen to be a solution to this equation. But that's the basic overall underlying thing for what homomorphisms are. Okay. Hello. There we go. Yep. So here we are at the second isomorphism theorem. So what's this? So this is a little bit trickier. So now we've got a group G Now we've got two subgroups of G, H and N. And one of them is normal, okay? N is normal. H is not necessarily normal, but N is normal, okay? Then the factor groups, NH/N and H/ the intersection of N and H, all right, have to be isomorphic. So this is very similar to the first isomorphic theorem. So if you actually go back to the first isomorphism theorem here, you see we're showing that this G/K and this H are isomorphic. And here we're just kind of taking it another step. And this diagram I've got here is called a Haas diagram, and it's kind of everything below. So as you go down, so G is actually there should be a dot at the top there. I forgot to make the dots, but G is the very top. Okay, then the first vertex is NH, and then the corners are N and H respectively, and then that next vertex is the intersection of N and H, and then the very bottom point is the identity. And as you go down the Haas diagram, everything is a subgroup of what was previously, what was above it. That kind of helps us understand sort of the statement of the theorem a little bit better. So let's define a mapping P, all right? This is where you might want to follow along in the book on page 143 a bit. P is going to be a mapping from H to NH/N, all right? And we want to basically show that this mapping is an epimorphism. So let's take an element of H, all right? We're going to call that, and we're going to call PH the coset NH of N in the subgroup NH, okay? P is obviously surjective, but it's also a homomorphism if you work it out, all right? Meaning it's got that, again, we'll go back here, it's got that basic form, FAB equals FAFB, okay? So, so we know it's a homomorphism, and and obviously, if it's an homomorphism, it's an epimorphism. Let K be the kernel of this. Okay, so again, the kernel is all this junk that gets mapped in. It's the set of everything that gets mapped into the identity. All right. So then, by the first isomorphism theorem, H/K is isomorphic to NHN. Now, to complete the proof, you got to prove that K is actually equal to the intersection of N and H. Meaning, what I should have probably done is tossed in where I have the intersection of N and H. I should say that equals K. That's what we're trying to prove. We're trying to prove that that vertex down there, the lowest vertex there, where the two paths come back together, that is K. Okay, that's the kernel. All right. Well, it's the kernel of P essentially, meaning it's the kernel of this function P. All right. Where the function takes, and it's taking stuff. It's basically, taking things and mapping it into the identity. Okay, so that's the basic gist of it. Essentially, what we're doing is in a way, I guess we're kind of decomposing G into pieces. Okay, you could kind of think of it that way. So, basic summary. That's essentially the gist of it. Just to quickly sum up, so the first thing is that this definition of what a homomorphism is. If you got this mapping from group G to group H, F is simply a homomorphism if FAB is equal to FAFB. Okay, period. One thing I do want to note, since you've all taken linear analysis, this is very similar to, in linear analysis, what we call a linear transformation. And in fact, that's exactly what we said a homomorphism was. We use the word homomorphism and isomorphism and everything in linear analysis. So a linear transformation, say you've got from a vector space V to a vector space W, and it's defined by f of A plus B, where A and B, I put lines over them, they are vectors. Okay, that's why I put a line over them to differentiate. they're equal to FA plus FB, okay? And F equals KA is KF times A for all A and B in some vector space V, okay? So that there's a very similar relationship here, okay? We're talking about a, I mean, essentially, it's almost essentially the same thing. It's just one's speaking in terms of vector spaces very specifically. The other one is very general to groups, just all groups. And then we defined the kernel as the set of all elements that map to the identity under a given homomorphism. And then we talked about a subgroup H as being normal in G if GHG inverse is an element of H for all elements of H. Okay? And G is an element of G. So those are kind of the big ideas to get out of this. We are going to come back to this because I'm fiddling with the schedule and I want to do some things on permutation groups. And so we're going to come back to cyclic and permutation groups a bit later because we're gonna take a look at Cayley's theorem. You'll get a better sense for why some of this stuff is important when we get there. But I hope that wraps things up and explains it a little bit better. If you have any questions, the big thing is that I think if you work through the homework problem that I assigned, which is number 5 there, on page 144 in Wallace, this quaternion group that has a Cayley table. First of all, you got to find the center. Then you've got to find all the subgroups of Q and construct a Haas diagram. Determine the conjugacy classes and then identify the group Q, ZQ. I'll make a quick note on conjugacy classes here. Let's see. Just going to give you a reference that you could look up. Conjugacy classes. Yeah. So you want to look at page 132. Basically, if you got an element that in the group G, the set of all elements that is that are conjugate to G. Say let A be an element in G. The set of all elements that's conjugate to A is the conjugacy class containing A. That's it. Okay, very simple. But you want to determine the conjugacy classes for that, which means you want to take E, A, B, C, D, F, G, and H, all of 8 of them. Okay. Each of them there ought to be a conjugacy class for each of them. All right, you got to figure out what those are, and then you should do the Haas diagram, and then you have to identify the group Q/ZQ. So the factor group QZQ. Okay, and I think if you do that, you'll have the basic idea of the things down that I wanted you to have down. And we'll talk maybe a little bit later in the week about where to go from here, whether we should have, because I have a test scheduled somewhere along here, and we'll see if this didn't help. I think the big thing is if we can try to get number 5 done as soon as possible, and then we can touch base via email or something in the next couple of days and see if we got that. So anyway, if you have any questions, send me an email, or we could set up a Skype or something like that, Yahoo Instant Messenger or whatever. And I hope everybody's enjoying their week. I'll talk to you later.